hardware involved. We'll start with the modeling, okay? And in the modeling part, I'm going to start with the physical systems. So here we have this mechatronic device, and this mechatronic device, it's a physical system. It doesn't understand digits, but certainly it's in the analog domain and it can function. So first of all, let us try to understand what do we mean by a physical system. We spoke of it a few times. What do we understand by a physical system? First of all, what is a system? Before we go even to a physical system. You have possibly studied in your thermodynamics course. A system can be considered as an abstract idea, as an entity which is separable from the rest of the universe by means of a physical or conceptual boundary. Okay? And second aspect of a system is that it should be composed of interacting parts. The parts within the system should be capable of interacting with each other. So we may say a human system, may say the digestive system, may say the circulatory system. Okay, what we are doing essentially is creating a boundary and separating that part from the rest of the universe. Okay? And we have to have, it should be composed of interacting parts. It's a system. It's composed of interacting parts and it's an entity separated from rest of the universe by means of a physical or conceptual boundary. Now, physical systems are those, okay, now we go a step further in systems. Say physical systems are those in which energy or power is transacted between their components. See, this is what makes a system a physical system. Whenever you are dealing with energy or power interacting between the components of a system, call it a physical system. Okay, you have information systems, but there you don't have transaction of energy or power. So in physical systems, this is the characteristic of physical systems. They obey the laws of physics because they're dealing with energy or power. Okay. Now, power can have diverse forms. It can be in several forms. We may have a mechanical form, electrical, electronic, thermal, chemical, fluid. Okay, different forms of power. And in physical systems, there is a very important aspect which we usually take for granted. And that aspect is called the aspect of causality. It's actually cause and effect relationship or an input-output relationship. So usually we don't take this, we take this aspect for granted and we don't deliberate much on it. We don't care much about it. But it's very, very important as far as physical systems are concerned, and things will become clearer to you and why it plays a significant role in the design of mechatronic systems. That will also become clear to you as we proceed with our course. So causality is an important aspect of physical systems. Okay, this cause and effect relationships or input-output. It is a cause and effect relationship between components of the physical system. Now, why are models needed? We said that we'll need a model of the device, and we need it in order to understand how this is going to behave. So models are needed to study and understand the behavior or response of a system when it is subject to various conditions. Okay. Secondly, to perform experiments or simulations and make measurements. So you could perform experiments or simulations, make measurements, and then check how your device is behaving. For design and testing, you could use a model for design and testing. Very important. Also for control of physical systems. And control of physical systems is a very important objective in engineering. You see, this is what distinguishes us from scientists, engineers from scientists. It's, scientists understand, they observe, they understand physics. Okay? What the engineers do is they design, okay, and make systems behave. They want them to behave. So they control the behavior of these systems. They have to, of course, understand the physics of the system. So the engineers have to go a step further, and it's very important. So this is the distinction between engineering and science. So here you have this aspect of engineering, which is control of physical systems. It's very important. Now, if you prepare a model, you are interested in making a mathematical model which the computer can very well understand today, you would like to also analyze the model, what kind of mathematics comes out of it, and possibly do some analysis on it. And also, in case it's too complex, if a theoretical analysis is too complex, you would like to simulate the system and see how the system behaves. Okay, so you require, for the analysis, you require systematic derivation of system equations. And for simulation on the computer, you need to do computer coding. So this is a very important aspect in understanding physical systems. So modeling of physical systems is therefore an essential requirement for studying the response of a system. So we can understand how a system is going to behave, how our device is going to behave, because it's a physical system. We can understand how it will behave if we have a model. Okay? That model may be physical or that model may be mathematical. Now, in today's world, we would prefer to have, at the beginning, we would prefer to have a digital model. So we would the digital computer, and we would like to have a model on our digital computer because of several features of the digital computer, because of its capabilities. What are those capabilities? First of all, it is programmable. So because it is programmable, we can just change its software. We can make changes in the software. So that is an advantage. We don't have to change hardware every time. So this is a very significant advantage of the digital computer. You can program it. It can be used for rapid execution of repetitive tasks. Imagine you doing the same task repetitively, okay, again and again and again. And if you're asked to do it very fast, I think you must have seen the movie by Charlie Chaplin. Okay, it was on the Industrial Revolution background, modern times, I suppose. So that's a beautiful way of how a human being can get bogged down in rapid execution of repetitive tasks. And here we are going to deal with really very fast execution of repetitive tasks. So the best candidate for executing this is our digital computer. And the digital computer can also interface. It can interface with peripherals and machines. So you can connect it, your programs, you can connect it to machines. Okay, it can be implemented in the form of robotics or in terms of machine tools, different ways. Okay, so it can be interfaced with peripherals and machines. And today, the digital computer is affordable. You can see that you can buy a cell phone today. There's a digital computer in it. You can buy a laptop. It's much more affordable than what it was a few decades ago. So certainly the popularity, the need for using a digital computer in preparing a model, that is strongly justified. And when we use the digital computer for preparing this model, we are stepping in the world of computer aided design. Now, conventionally, you must be having the idea that when we say CAD, we are talking of AutoCAD or SolidWorks, or CATIA, software like that. But those are software which are used for solids modeling. Okay, you can prepare drawings, you can prepare, you can model objects geometrically. Okay, you have to have something more with those packages. You have to have features for analysis, which they of course incorporate today. So you have to have analysis and aspects for design. Now they have sufficient tools. They have a good number of tools for analysis and also a significant number of tools for design. But they don't cover a significantly large spectrum which is needed in today's world. So it's not just restricted. CAD is not just restricted to these software, these few solids modeling software only. CAD, computer aided design, involves a number of other aspects. Okay, we are familiar with some of the commercially available software. They are used for drawings and material specifications. And one can also do planning of processes based on this, estimation, what's the cost going to be, integration with manufacturing, automation, inventory monitoring and control, costing, uh, and marketing. Of course, when we logistics also is included in all this, and managing everything together after all that, so that comes under enterprise. We have software for it, enterprise resource, ERP systems. You are already familiar with that. Now, the systems, the physical system which we are going to deal with, if we are to understand how it is going to behave, we should be able to specify what do we mean by this behavior. This behavior is expressed in terms of states. Okay, so state determined systems. You say that these states are associated with this system. And when we know how these states change, we know the behavior of this system. So we make use of state variables. These states, they are represented by state variables. These are actually a minimum number of variables which are required to describe the behavior of a system completely. One can derive system equations from these physical systems. The models are usually prepared as system equations, and because you're dealing with changes, okay, dynamic systems are dynamic, so you have to represent them using ordinary differential equations. Okay, now why do we use ordinary differential equations for representing dynamics? It's because we are dealing with rates of change of the states. So what is the rate at which these states change? And these rates may change with time. So what is the rate at which these states change with time? So the rate of change of states, naturally, when you talk of rate of change, that means you're talking of a time derivative with respect to time. derivative of the state with respect to time, and equations, representations of these derivatives. Okay, so we are dealing with ordinary differential equations, something which you have already done in your mathematics course. And then we also have constraints. We have constraints in the form of algebraic equations and in other forms as well, but usually we take them in the form of algebraic equations. And we also have outputs. Okay, so system equations, they are represented using these. We have linear systems, which are the theory of which is very well developed today. And we have nonlinear systems, which are not fully understood or which are understood little. And you can't use the theory of linear systems to understand the theory of nonlinear systems. So many times, okay, except in the simplest cases, one has to resort to simulation, numerical simulation. So you need a model, certainly, and you have to simulate that model. So these are the various aspects. Now, we did speak of the necessity of dynamic models, but what are the aspects where we use it? Use it for analysis. So these models of our physical system, of our mechatronic system, we'll be using it for analysis. What do we mean by analysis? Means that given input future history, it means if you are providing the future history of the input and the initial conditions, you are determining the output. How is the system, what output is the system going to produce if you provide these inputs? Identification. So dynamic models are also used for identification. Identification is given the input history and the output history, you are determining the system. What is the system? So you are constructing a model of the system from the inputs and the outputs, which both of which are known. You are determining what is the system. This is identification. Then you have synthesis. So given the input future history and some desired output history, determining the system so that the input to it will produce the desired output. Okay, it's synthesis. You're synthesizing it. You're synthesizing a system in order to get a desired output for a given input. And of course, control. In control, you're given the system and determining the inputs. What should be the inputs so that it will produce the desired output? Okay, so maybe there are subtle differences, but these are broadly the uses of dynamic models. And we will come to a technique which is graphical in nature. It will be used for modeling of physical systems, physical system dynamics. The reason for this is it will become clear to you as we pose these few questions before you. Are pictures and graphs easier to understand than equations? Suppose you wanted to understand a physical system. You have pictures and graphs, or you have equations. Which one is easier to understand? Except for the simplest cases, I'm sure one finds it difficult to understand equations. It's rather easier to understand pictures and graphs. Okay. Secondly, now if one can understand physics, the pictorial representation of systems, can mathematical features of dynamics be represented pictorially in the form of pictures? Can one represent the dynamics? Can one model a system in terms of a picture? That is a question that arises. Now, suppose you are able to do that. Can the graphical modeling methodology be employed to any energy domain? If you are able to construct a graphical model, let's say, will it be restricted only to electrical systems or only to mechanical systems or only chemical systems? Can we have a methodology that can be applied to any energy domain? Okay. Can system equations be derived easily from a pictorial model? Now you have got a graphical model. You are also interested in knowing, what would be its analytical output? What would be the equations coming out from that model? Can you derive the equations from that model? How to simulate this model of a dynamic system in an easy manner? So suppose we have this graphical model. How do we simulate this model in an easy manner? Can simulation code be derived automatically? Suppose we have this model, can we systematically obtain the simulation code from that model? Can we program it so that a machine does this part for us automatically, derive this simulation code so that we don't have to worry much? We just make the graphical model and automatically the simulation code is produced. Can a pictorial model offer insight into analysis for design and control? Okay. So you make a graphical representation. Is it going to offer you insight into the analysis for design and control? So very important aspect. If it can do that, wonderful. The answer to all these questions is a graphical approach called as bond graph. It's a unified approach to the modeling of physical system dynamics. Okay, and we are going to explore this, and it is widely used in mechatronic devices, in mechatronics today. And there may be other tools, but bond graph is very, very powerful. There is no restriction on linearity or non-linearity. You can apply to any system, any energy domain, any physical system in any energy domain. And that is the advantage of bond graph. Okay, it can be employed to any energy domain, and the same graphical technique. Here we have an example of an electromechanical system. In this case, it's a DC motor. You can see the rotor of this motor. You can see the commutator brushes, and of course, there are permanent magnet. The field is produced using permanent magnets, and here you have the winding. So the resistance of the winding and the amount of the winding is represented discretely here. You are applying a potential difference. You are applying a source, potential source here across. So this is going to rotate, and depending upon the flow of the direction of the flow of the current, you're going to have the direction of the rotation, which will be determined. Okay. So what it essentially does is it converts the current to a torque, to an output torque, and we will see the principle of DC motor in our subsequent lectures, and how we model it using bond graph as well. So here we have a graph, a graphical representation. Maybe it looks too cluttered for you at the moment, but let me just explain. What we have got are peculiar arrows here. These are power arrows, and what we mean by these power arrows we will understand subsequently. Here is source of effort, which we call as which is this voltage VT, and it is providing power to this system. Here we have got a junction. It's a one junction. Things will become clear to you. Just try to figure out at the moment. Some power which was input to this junction, a part of it goes to the resistance, a part of it goes to the inductance, and the remaining part goes in towards the mechanical system, from the electrical system to the mechanical system, where current is being converted to torque. Okay, and you have, on account of the application of the torque, you have the rotation of the rotor. So you have the angular momentum of the rotor which would change, and you could also model the bearings, the resistance of the bearings over here. So you have a model, you have a graphical model. And what this graphical model is doing, you can see just it's putting in power here and doing a distribution of the power. It's showing where all this power is going. Okay, what is this effect and where all it's going? That's all. And using this simple mechanism, simple representation, you can proceed to construct a model. You can, so this is how this model looks graphically. Now, this technique, I'll give a brief introduction of this. It's called bond graph. And it was invented in 1959. In fact, it was disseminated in 1959 by its inventor, Professor Henry Painter. He was at MIT when he propounded this idea. And he was an assistant professor in the Department of Civil Engineering at that time. And of course, he became a professor of mechanical engineering at MIT later as well. So he was a professor of both civil as well as mechanical. This is how he looked years later, after 1959. So it's this technique, which was designed by him, is a pictorial representation for physical system dynamics. You are able to represent physical systems using a grammar, using a language which is pictorial. Okay? It's very simple. It makes use of a power bond. The bond which you saw, which was a half arrow, which looked like a harpoon arrow, was a power bond. And it represents a power transaction. And a power transaction is actually caused by the product of two variables, an effort variable and a flow variable. Professor Henry Painter also came out with the elements for representation of physical systems. He came out with the junctions, elements, and connections, and with cause and effect, representation of cause and effect, causality, which we discussed some time back. Things will become more clear to you as we go deeper into our course. So these were his significant contributions. And bond graph modeling of physical system dynamics, today, why we do it? Because it's a graphical representation of dynamics, easier to understand. It offers insight into the physics of the system. It can be applied uniformly to multi-energy domains. It represents the interaction of power between elements of the system. It represents cause and effect relationships, causality. Okay? And the most useful aspect is that algorithmically you can derive system equations in a form which is called as a first order state space form. And that's very useful for numerical integration, which is required for simulation, okay, using numerical techniques, as well as for modern control theory when you want to design control systems. It's also used for coding, for simulation. And one can modify a bond graph, one can append, delete, depending upon what phenomena you want to include, what you want to exclude. And it helps in developing control strategies, and several of those impedance control strategy, overwhelming strategy, and study of structural control properties. In France, they have done a lot of work on this. Fault identification and diagnosis, they have done a lot of work on this. So all this using the graphical approach of physical system dynamic modeling using bond graph. There are a number of software that are available. CAMG, 20sim. 20sim is by far the most popular today. There was a very powerful software called Symbols, which was originated in India. Um, an older version is available even today. There were other software, Amesim. Um, Symbols was, of course, very powerful. Um, but in our group, in our department, we do not use these software because then there's a tendency of getting dependent on this software, and we lose our sight of we lose our ability to invent on our own. And so we have adopted the use of MATLAB or Scilab, and we do our coding for simulation based on this. And it's very simple. Once you understand it, things will become very clear to you. So it's easy to program, and all control lies with the modeler. So, you're not slave to any of these commercially available software. It's easy to modify, easy to append, etc. So, we will conclude our lecture here for today after we see whether you have queries. So please let me know if you have any queries. If you don't, then I'll conclude the lecture here.